This is the system configuration comprised of 25 piezoelectric sensors. The size of the piezoelectric sensor node is 41 millimeter. The connections of the sensors are connected in parallel series connection. So as you can see here, the pressure is applied on the upper tile of the piezoelectric sensor. We have an output, 2 wires coming out of the matrix, inserted to the PCB, which is our system configuration. So the first component that we have is full wave bridge rectifier. Full wave bridge rectifier will convert the signal from AC to DC. Then we have a capacitor to reduce the ripple effect. After that, we have to store the output voltage that's coming out of the matrix in a battery. The battery, the size of it is a lithium-ion battery of size of 3.5 volt, inserted to the boost converter. The boost converter will boost up the voltage to 5 volts, as you could see here, and so we could charge a cell phone. So as you could see here from the PCB, we have a multi-output that you could get it from the system itself.
We take another 2 wires, positive and negative, to connect it with a voltage divider, then connected with the Arduino to measure the output voltage that comes from the boost converter. As well, we connect temperature and humidity sensor to the Arduino. After that, we connect USB port to the PC to take both the temperature and humidity sensor and output voltage in the Arduino application.
Okay. So as you can see here, this is the code applied to the Arduino application. So we could get the results of the output temperature, humidity, and output voltage. As you could see here, the readings is the temperature is 22 Celsius and the humidity is 95%, and the output voltage is 5 volt at the desired output voltage that we need. So the system then, we take the data from the Arduino and connect it by the API key to the things it speaks. So the data could be stored in the cloud. So this is the readings, as you could see here. This is the temperature and humidity, and this is a graph of it and some of the readings that we get. So after that, from this stage, the data will go from cloud to the blockchain.
This is after the integration of the JSON file, which contains the readings of temperature, humidity, and voltage in a structure that is usable by the SIEM solution and blockchain system. Essentially, the data was stored in cloud and then moved to blockchain to ensure secure storing. Now the SIEM, while the solution is a platform that allows us to see the attacks and alerts taking place in real time, and it also allows us to visualize the system's security status. We are now looking at the system having the JSON file without any attack initiated. Now we will move to the computer that generates an anomaly attack. Here we will generate the attack using using nmap sn command and the IP address of the device that we are targeting. That is, after successful initiation of the attack, this is our new dashboard. We can see that there is an anomaly attack here. It shows that there has been an anomaly attack that took place as this portion. We can also have a look at the alert groups evaluation that shows a rise or a spike that indicates some attack happening. We can look at the alerts that have been encountered and the top 5 rule groups. Also, a more detailed section is here about the attack that happened in a table and providing the JSON file as well. Thank you.
Today we'll be looking at the code for the blockchain project, followed by a demonstration of how the code works. This Python-based blockchain implementation is tailored for storing and managing data obtained from a JSON file containing temperature, humidity, and voltage readings. The system captures and organizes the data into blocks, each encapsulating specific readings alongside timestamps and the unique identifiers. Through a mining mechanism, new blocks will be continuously appended to the chain, validating transactions and maintaining the integrity of the data. The block.py file class implements the algorithm proof of work and the SHA-256 hashing algorithm or hashing function. It's a function to create the hash based on block attributes. Each block object essentially stores the data itself, including a block number or an index, transaction to be held inside, and a timestamp. The previous hash is very important because it is what makes the blockchain immutable. Every single block contains a reference to the block that immediately preceded it, making the blockchain immutable. If we were to change the hash of a particular block, we would have then to recompute the hashes for all of the blocks that follows it, which is computationally expensive. The blockchain.py file has two algorithms. One of them is the proof of work algorithm defined here. This method is it ensures that the defined difficulty for mining is established by verifying if the resulting hash for the block meets a specific criteria. The consensus algorithm used here is find the longest chain. It's called find the longest chain method. I have it here, which implements the consensus by checking other nodes chains and adopting a longer valid chain if found. The add to transaction method ensures that the data has been received from the JSON file, essentially from the cloud, and it ensures that the proof of work algorithm is satisfied, because only then the block would be allowed to be appended and to print out a success message for that particular block. Finally, we have our string method that cycles through the entire blockchain to print out every single one of them at the end with their hash IDs and the timestamps and the block data itself. This is the JSON format. This is a quick implementation for the blockchain entire project. When I run the main.py file, the add Genesis block as an initiation or for instantiating the blockchain system all together is printed in block number 0 or index 0 to indicate that at the beginning of the blockchain. Then each transaction is added. Each transaction refers to a block from JSON containing temperature, humidity, and voltage in Celsius and temperature in Celsius and Fahrenheit. Each block is then retrieved after being added to the blockchain. I have set this project to retrieve back all of the stored blocks in the blockchain. Index 0 being the instantiation block, which is Genesis block, and each one, and then the following ones are the data itself. We can see the index, the hash, the timestamp, and the block information itself. I have in my sample file, I have 20 different blocks for 20 different readings directly from the system. So it will print out all of the retrieved blocks from the blockchain. And this wraps up the blockchain implementation. The next phase of this project is taking this data into SIEM and seeing how how it is well secured, and monitoring it in terms of the attacks and the threats that are directly influencing it.